Okay. Let me just put that down to post home assignment. Okay, so let me just pull up the exam. I can't show you everything at the same time, but I'll show you what I can. Okay, so the first question that people started kind of where problems started arising for a couple people was on Bessel's correction. And this is, I admit that this is just a hard concept to feel very confident about, but I think it can make some more sense. So Bessel's correction, the question was, what is Bessel? The first one was, what is Bessel's correction? Okay, so normally when we're doing formulas with a sample, we're doing things, you know, like if we have the mean, we're going to sum up all the xi's and we're going to divide by the sample size. When we do a variance calculation, we do something funny, which is that we subtract 1 from the sample size. And this is called Bessel's correction. Okay. Sum of xi minus x bar squared. And the key here is that this number is a goofy number because it's shaped significantly by each of the xi's. So the sample mean is probably not the same as the true population mean. And so what that means is that our estimate of variance is systematically too small in small samples. I'm sorry, yeah, in small samples. So what we do is we divide by n minus 1 rather than n, and that makes our estimate of the variance somewhat larger than it would otherwise be. So Bessel's correction is just a way of being conservative and putting a little bit, boosting our estimate of variance up a little bit so that we're not underestimating the amount of variance in a data set. So what was the correct answer? Actually, 3/4 of you guys got this right. So it's in small samples. The sample mean will be artificially close to each element, making our estimate of the variance inaccurately small. So the best decoy was this one. It says, in small samples, the sample mean will be artificially far from each element, making our estimate of the variance inaccurately small. So there are a couple reasons that can't be true. One is that if the sample mean is artificially far from each of the data points, that would actually make the variance larger. So it's not, it could, even like within the statement, it's impossible. You can't make the distance between the mean and each piece further apart and somehow be making the variance smaller. So it's kind of a contradiction inside itself. And then actually the other thing that you could know is that the sample mean isn't artificially far from the data, it's artificially close. And you can just think about it like, say you rolled the die twice and you got a 5 and a 5, or a 5 and a 6. And so from that 5 and a 6, from this small sample, you estimate a sample mean, which would be 5.5. The true population mean of a dice is usually 3.5. Okay, so that if you roll 1,000 dice, on average you'll roll a 3.5. But both the 5 is going to be closer to 5.5 than it would be to 3.5, and the 6 will be closer to 5.5 than it would be to 3.5. So the sample mean in a small sample is going to be artificially close to each of the data points that are in our sample. Does that make any better sense? Does that click for anybody that felt uncomfortable with this question before? Danielson, Derek, Devin, Esmeralda, Ibrahim. And I should just say this is a really nice time to learn this material because we've seen it before. And I will just be honest that the Bessel's correction is super unintuitive. I think it really, okay, makes more sense. Okay, this is just worth like sitting down and thinking through this a couple different ways. Like do an example where you have a small sample and a large sample and where you know what the population mean is. So do the dice example. If you want to understand this, do the dice example. You know what 3.5 is. Get a bunch of roll a bunch just on your desk, roll two die and calculate the sample mean, calculate the sample variance and see that you're systematically going to be getting a number that's too small because the mean is not the right mean. But this is a really good time to marshal your attention because you've seen it before, and then you've had this test just recently, so you can kind of remember what you were thinking when you were going through this process. Okay, then the very next question was also was not, I mean, 73% got it right. It was in large samples, Bessel's correction is, and the correct answer was not important. And then the best decoy was that it's especially important. So that was the answer that tricked the most people, is that Bessel's correction is either especially important or not important, especially important in a large sample. The reason that it's not important in a large sample is because, watch this. So the normal thing that we have is 1 over n. And what do we know about 1 over n as n gets large? As n gets large, what happens to this number right here? It gradually approaches 0. So as I put an n in there that's larger and larger and larger, this fraction will get smaller and smaller and smaller. Soon I'll be dividing by 1 over 100, and then 1 over 1,000, and 1 over 1,000,000, and 1 over 1,000,000,000,000. And eventually this number it approximates 0. So this is interesting. What happens to Bessel's correction as n gets large? The answer is the same thing. It also approaches 0 at about the same rate. So in either way, as n gets large, this small adjustment, n minus 1, becomes a smaller and smaller deal. So if I have a data set even of 1,000 people, and I did the variance with Bessel's correction and the variance without Bessel's correction, I couldn't tell the difference between those two variance estimates very easily. So as the sample gets larger and larger, Bessel's correction becomes less and less important. You know that's true because n is in the denominator, and as the denominator gets large, the number itself gets very small. Okay? Questions there? Okay, you guys got them. So most of, I think last time I taught this class, when I asked the mean and the standard deviation, many people got it wrong. Only 2 people got that wrong this time, so that's great. So some things are coming through really clearly. What's the formula for covariance? You guys all got that right, basically. What is the variance between x and itself? So this question I'm going to throw out and give everyone an additional point because of this question. The question ought to have been, what is the covariance between X and itself? Either way, I think you could have gotten the right answer, but it was poorly worded on my part. And so the answer was the variance of X. So actually it's true that the variance between X and itself is the variance. The best decoy there was that 0, that nothing varies with itself, but that's not true. Covariance is the measure basically of how X varies with itself. So I think that was possible to get right, but I botched important part of the wording. So everyone will get an additional point for that. Okay. Okay, you guys got that one right. Okay, this is a good one that a good number got wrong. So let me clear my slate. Okay. So one of the questions was, and this one, 64% got right, but I just wrote this I think is a nice, just like application of what we have. So remember, we did some summation properties, and one of the summation properties is that if I add up all of the xi's, it's the same from 1 to n. It's the same as the n times the average of x. So we did this proof together in class where we had, I'll just show it to you really quick so that it can ring a bell. So here's the proof. We start with the sum of xi is equal to what? What we can do is we can multiply this by 1. So remember, multiplying anything by 1 preserves it. So we're going to say n times 1 over n, because notice that this is just 1, is times xi. Okay, so all we're doing is I'm pre-multiplying this summation by 1. And then I'm going to notice that n, this is equal to n times 1 over n, the sum of xi's. And I can notice that this right here is just the average of x. So to sum all the xi's is equal to multiplying the average of x by the sample size. And I think I gave this exact example in class. I said, what if I gave you the mean income in the country, and I gave you how many people there were in the country? You could calculate the whole income, whole earnings of the country by multiplying the mean by the number of people that are in the country. So that's a really useful thing, that from a mean you can gain all the information about what's the aggregate of a place. If I gave you the mean number of hours that UC Merced students study, and I told you how many students there were at UC Merced, you could calculate how much studying, how many hours of studying were taking place every day. So you can always get the aggregate from the mean if you have the population size. Any questions on that one? So here's a question, a variant of this question that I could put on the final, which is, if someone told you the median earnings in the US, how would you calculate the total earnings? And the answer would be that you can't. The median and the mean won't be the same. And so you even if I give you the median and how many people there are in the country, you don't have enough information to find the total. Let me stop there for questions. Leanna, Kimberly, Luis, Manuel. Awesome. That's great. Okay. Yeah, break in and tell me when something goes awry, because I'm sure that other people are having the same thoughts that you are. Okay. The next question was, okay. So this one, about 60% got right. And this was how the question was written. It was, if I estimate a best fit line by ordinary least squares and calculate the error, so remember that the error is each y minus the predicted y. That is equal to yi minus beta naught hat. Okay, and that's just because, so how do we get from there here to there? It's because y hat is equal to beta hat plus beta 1 hat x1. Okay. So I just want to make sure that step's crystal. And then, remember that we did a couple examples where we summed up. So when we summed up all the UIs, it always equals 0. And to emphasize it in the slides, I wrote it like this. I just kept doing a big circle. So I was trying to say it's always 0. And this question and the next question are related. But the reason for this, I think you can think of this intuitively. Why are the errors 0? Imagine that we had a data set, simple data set. Simple data set going through there. I did this line badly. Let me try one more time. If you just kind of eyeball it, there are basically as much space above the line between the data points in the line as below the line. And I'll show you in the very next question that that's built into how we select beta naught and beta 1. So actually watch this. Let me draw the wrong line just to show you this point another way. So imagine that I drew a new line through these data points. It was like this. I mean, what I'm trying to do is make it clear that if I put the line too high, we'll have all the error terms on one side will be larger than the error terms on the other side. So these will all these error terms will be negative. And I could do a different line. I'm sorry, let me pause right there. So all these error terms will be negative. So it means that we've drawn our regression line too high. And we can improve the fit by pushing down beta naught. So remember, beta naught is the y-intercept. Watch this. If all we did is we pushed down the y-intercept of this line, we can get it to go all the way through all these points. They're going to be small. The distance between the points and the line will be made smaller, so it's a better fitting model. So whenever we get, if ever we did our regression and we added up all of the errors and we found that it wasn't equal to 0, we would know that we could change beta naught to improve the fit of the line. So let me just do one more example. We did this line that was too high. we could imagine a line that's too low. And here, when we draw the errors, you're going to notice that all the errors are going to be positive. And so if we summed up all these errors, we wouldn't get 0, we would get something too big. And so what do we know? If all we did is we pumped up the x-intercept, the y-intercept, excuse me, a little bit, we could send that same sloped line through the middle of the points. So the correct line, the regression line that minimizes the distance between the lines, the line itself and the points, will always go through their middle. And because it's going through their middle, there are as many data points above as below the line. Or rather, the distance between the points above it and the line and the points below it and the line is the same. Let me just stop there because that's a really important. And I try to, and I'm hoping that did something too. Did that clarify anything for anybody? Yesenia, Warren, Stephanie, Saul, Noah, Manuel. Okay. Okay, cool. So a related, it's almost the same thought is, why is that? Let me show you why that is. So the very next question, so I kind of thought I was like being helpful by giving the next question something that could help you. The next question said, when we take the first derivative of the sum of squared errors, we find the first order condition. So remember, when we want beta naught and beta 1 to minimize the sum of the squared errors. So remember that the error is equal to this up here. But we can, the derivative of that, the derivative of the sum of squared errors will be, with respect to beta naught, will be this, and I give this to you in the question. Just making sure I write it the same so that if you go back, you'll have it in the same. So why is this equal to 0? Because at the point where we've selected the right betas, the distance between the line and all the other data will be minimized, which means that its derivative will be 0. So remember the derivative, we had a function like this, and we want to know where's the minimum. We're going to look for where the space is flat. And where the space is flat, the function is minimized. Okay, so that's true. Now, so this is a condition. This is something that we're imposing on beta naught and beta 1, that this function needs to satisfy this condition. Therefore, if when we sum up yi minus beta naught minus beta 1 x1 with our estimated values, we'll get 0. And if you notice what this is the same as ui. So the sum of the errors is equal to 0. And so if the sum of all the errors is equal to 0 and we want to know what's the average ui, well, what's the average of summing up 1 over n times the sum of ui is going to be 1 over n times 0, which will be 0. So it's really the same question as before. It's just once you notice that the errors, when you sum them all up, they equal 0. That's both of these questions basically. So, it's the exact same idea. You need the beta naught to shift up or down that slope so that the line is going through the middle of the points. Okay. So we kind of showed that two ways. We showed that with this function, with the first order condition. We showed it with an example in class when we added up all the error terms. And we've showed it with a graph where I just showed you if it's not going through the points, then the error terms are not going to sum up to 0. Okay, so questions here. Cameron, Denelson, Derek, Devin, Esmeralda, Ibrahim. Okay. Okay, so the next one was when the rescaling question on mentoring. Let me see if I can find that. So the question was, say that we estimated a model and found wages are equal to 5 plus 6 times the mentoring binary variable. And we rescale mentoring in terms of months of mentoring rather than a binary variable. So our new variable will be months mentored, and that will be 6 times the mentoring binary. Okay. So remember, we had a formula for this. We said we know that our old beta 1 hat will be covariance between x and y divided by the variance of x. And the question is, what happens now? Multiply x by a constant called a. What does the new, so we say it's new with a star, everything new is shiny. And we just do the same exact formula where we have covariance times a of a times x plus y over the variance of a times x. Okay, and so you didn't need to do all this work, but I'm just going to show you where it comes from again. A can come out as a, and a constant comes out of a variance as the constant squared. Okay, so this is equal to a times covariance of x and y over a squared. I'm going to cancel out the a with the squared term, variance of x. And then we can notice that this right here is actually our original beta. Our original beta is just hiding right there. And so then we can go, we find that this is equal, the new beta is equal to 1 over a um, 1 over a times the old beta, the original beta. So here in our example, we multiplied, in this question, we multiplied our x variable, mentoring, I number 6. So that's our constant, okay? So what do we know? And we know that the old beta, the original beta was 6. So the question is, what is the new beta? And we can do it really simply by just taking 1 over A times the original beta. Okay. Any questions on that? The rescaling stuff wasn't a huge part of the test. It's important, but it's not. It wasn't supposed to be tricky. It wasn't supposed to be a trick. The decoy on this one was 6, which I think means either that the question wasn't read super carefully, because the question is in bold at the bottom. What is the new beta? It's obviously not what's the original. I would hope it's not what the original beta was. And then just that simple formula that we have right here. Put it in. Okay. Questions there? Okay, let me see where we are. I feel like there's a little bit of drift. I think people are tired. Should we do a quick break and come back? Is that right? Am I reading the room right? Okay. I will be back in like 2 minutes, and I'll show you a funny video, and hopefully, and then we'll get back into this. It's taking a little longer than I thought, but I think it is really, really good. I think that if we can get this stuff down pat, I think the second half of this block will be a lot more pleasant and a lot easier for you guys. So I just want to take our time and get through this. Okay. Good. If you think it's helpful, then I'm very, very, very happy to do it. Oh yeah, go get breakfast, Leanna. Come on, gotta get some breakfast. Okay, I'll be right back. Okay, let me share this screen. I'll show you a little funny video. You probably learned that I like comedians. I think that it's kind of an ancient archetype, you know, the court gesture in these ancient Arthurian tales and things. Roman are they're kind of truth tellers. They tell the truth in a funny way, or so I just think that that's kind of a deep part of the human spirit, is to speak truth in difficult topics through humor. I don't know where I've put it. This one, it doesn't have anything kind of deep in it, I don't think, but it's kind of funny. Nice control landlord. Can you guys hear? And one question I have is, when I show these videos, do they come in super choppy for you? No, they're okay? Okay. Sometimes I feel like the words are off kilter with the.
You know that old myth that professional swimmers eat 10,000 calories a day?
Okay.
I put a sign up which said, "Have you seen this cat?"
Apple wants me to buy a new computer, but I don't have any money.
Sign up which said, "Have you seen this cat?" with a picture underneath it that is clearly a fox. Missing from the area, answers to the name of Samantha Peterson. Any information to Peter at peterpeterson@gmail.com. I just made up these things. Until a couple of days later, I got an email from Carol. Carol wrote, "Mr. Lycett, it has come to our attention that you have a sign for a lost cat in your office door snap frame. May I remind you that it states in your contract that we have a strict policy on animals in the building, as this is a workplace. Animals are not permitted, and anyone found with animals in their units could have their contract terminated. Regards, Carol, management assistant." First of all, I checked the contract, nothing in there about animals, so she's got nothing on me. Second of all, it's a picture of a fox, Carol. I replied, "Hello, Carol. My apologies. There has been a simple misunderstanding. There is indeed a sign for a lost cat in the snap frame, but Samantha Peterson is not my cat. I am attempting to find her, as I believe she has been stealing from me." I popped into the office late one night last week and discovered that my collection of antique biscuits had been disturbed. Outside the building, I spotted a cat and instinctively shouted, "Samantha Peterson!" The cat turned, and so I deduced that is her name. I know she has my biscuits. Any help you can provide would be most appreciated. Many thanks, Joe Lycett. Carol sent me a reply. "Mr. Lycett, I'm sorry to hear about the disruption at your office, but I would like to politely ask you to take the sign down. The surrounding businesses have made complaints that their clients are being disturbed by your sign." Regards, how you can be disturbed by a sign, I don't know. She sent me another email straight after. She said, "Also, can I ask what the Peter Peterson email address is on the sign? Are you sharing the office space? Because it's a sole occupancy." I replied, "Hello, Carol. No, Peter is my private investigator. He's agreed to live in the office and work on this case for as long as is necessary." This sign with my compliments. Many thanks, Joe. I replaced the sign with the same picture of a fox, just with "wanted dead or alive" over it. Day later, another email from Carol. "Mr. Lycett, we've had more complaints that you've replaced the sign with a very similar sign. Also, you can't have anyone living in your office. Is there a time we can speak on the phone today? It would be easier to discuss this rather than over email. Regards, Carol." I didn't want to speak to her over the phone, so I replied, "Carol, I'm afraid that will not be possible. I have been advised by Peter Peterson that I shouldn't use the phone as it could be bugged." She replied, okay, Mr. Lassett, I just had one of our security guys go around and there is no one answering the door and the lights appear to be off. So I'm fairly confident your investigator isn't living in the office. As long as you don't have pets in the office, I'm happy to forget the whole thing. Regards, Carol. Very diplomatic, very considerate on Carol's part. I replied, Carol, Carol, Carol. Of course your security man didn't spot Peter Peterson. He is a private investigator. He lives in the cracks. He's watching you when you least expect it. He lives in the shadows of your darkest fears. In your weakest moments when you're naked and vulnerable, he's there, watching, waiting, protecting. He lives through all of us, within us, beside us. He's the breath on the back of your neck, the breeze in your hair, the moisture in the air. Cheers, Jay.
Oh shoot! There's a very funny part at the very end.
In a tribal ceremony. I took the sign down this morning.
I'm sorry. This is it. It's going so slow, but basically,
Carol replied, "Thank you."
Sorry, the end is really funny. He says in his email.
Why is it green?
Because he's not with this earth.
The green is the color of earth. That's what's left.
He says P.S. in his email to Carol. He says P.S. I found Samantha Peterson last night, and I sacrificed her to our beloved gods. So I've taken down the sign. And she says, as she replies, "Thank you." So he's very funny. Okay. Let's go back to our review. Let's see. Okay. So then one question that was incorrectly responded that is just should be totally easy was this one. It was, what is this a formula for? And the formula was yi minus beta naught minus beta 1 x1. Okay. And the correct answer is that this is ui, which we also call the predicted residuals. Why is it predicted? Because these, this is essentially our y hat, which is our predicted y. And so yi minus y hat is equal to the predicted residuals. For the error term, for u, these are all the same thing. So that one is just like a formula. About 60 or 55% got that right. Just over half the class got that right. And then the two alternatives were equally distracting. One was that it was the derivative of what I don't know. And then the other was the predicted values. So, but you know that this isn't the predicted value. In part, how do you know it's not the predicted value? Well, here's how you know. This is the predicted value. The predicted value is this. Predicted value is equal to beta naught plus beta 1 x1. That's the predicted value. So you know that this isn't the predicted value because this smaller thing here, this smaller thing here is the predicted value. So just this part is the predicted value. Okay. Okay, so then not a super complicated one, but just a good one to make sure that it's like kind of review that. Okay. This was This is good. So one thing I worry about is there are 16 students in this class logged in. I kind of worry that when there are 6 kids that get it wrong, it's the 6 kids that aren't here. So this is boring also. I can speed up and go to things that had more people missing them, but this one, less than 2/3, over a third got it wrong. So this is just, the question was, we have college graduate is equal to beta naught plus beta 1 times female. Okay. And the question is, what's the omitted category? And the answer was males. So males was the correct answer. Males were omitted. So it's not that they're not in the data. It's not even that they're not included in the regression. It's just that we have a beta for female and we don't have a beta for males. So so male is the omitted category. The best decoy was people who didn't graduate. And people who didn't graduate isn't an omitted category. So when we're talking about omitted categories, what we mean is who is implicitly in the data that we don't have a coefficient for. And they're in, so actually we'll come to this, but the average college graduation for men is beta naught, and the average college graduation rate for women is beta naught plus beta 1. Okay, so call graduation rate for men is just this. You just go beta naught plus beta 1 times female equals 0. It's just beta naught. College graduation rate for women is beta naught plus beta 1 times female equals 1. So it's beta naught plus beta 1. So one thing that you'll just notice is that whenever you have an omitted category, men or blacks or whites or Hispanics or females or non-smokers or whatever it is, that the average outcome variable for the omitted category is always just the intercept. That's always who is described by the intercept, the omitted category. Okay. Okay, the next one was okay. The next one's okay. Okay, this is a good one. So we did do this in class a couple times. And the question was, what if y has a curved, let me see here. So it's specifically who we want out. Can you say it again? Can you say it another way? The omitted category is who we want out. Is that right?
Yeah, for the people who are omitted, we just look for who's specifically out.
Yeah, who's not named, who's not,
Okay.
who doesn't have a variable describing their group is the omitted category. And it doesn't mean they're less important or anything like that. It's just they're the comparison, implicitly the comparison group. So men, if they're not included in the regression, they're implicitly the comparison for female. Can you over number 32? I actually don't have the numbers. What question was question 32? They just come without numbers for me for some reason. In this example, how much more does a person tend to earn if they were raised with cohabiting parents? Okay. So I think that the correct answer, you can tell me if I'm wrong, is is 2. So let me, this is when I did this problem, this is what I get. I get y is equal to 5.5 plus 2 times cohabiting. Is that right? Is this the equation you guys get?
Can you go over like the whole part of that? I'm kind of confused, like how you get there.
Sure. So, okay. So we've got, I mean, it's just a longish problem, so we've got to go back a little ways. So we've got, do you want me to do every step of it?
No, just like the 5.5, is it like the y-intercept?
The 5.5 is the what?
Is
The
the
y-intercept.
5.5 the y-intercept?
Yes, exactly.
Oh, okay. I think I know how to get there.
Okay.
Yeah, I was just kind of confused about that.
Yeah, so I'm not going to throw them all out, but I'm going to also throw out this last one that was asked about in this example. How much more does a person tend to earn if they were raised with cohabiting parents? So, if my check work was right, the right answer is not here. So I'm going to give everyone 2 additional points, one for this and one for the other one that we talked about maybe 10 minutes before we had a break. Those are the only 2 that I found mistakes in. So if you found mistakes in other places, you can send me an email or put them in chat or tell me after class. But those are the only 2 that I found mistakes in, and those, so they are not going to affect your grade. Everyone gets an extra point for those 2 questions. Okay. And yeah, I think the correct answer here was 2. There is no answer, like there was a no answer option, which I think was supposed. Oh, but no. There wasn't a none of the above. So that was purely my mistake. Okay. Let's see. Okay. So say we have a curved relationship. Y has a curved relationship with X. Okay. So if we try to do, say this is, wages, and this is experience, and we did this example in our slides for, maybe we had 5 slides on it or something like that. If we try to fit this with a regression line, a straight line is just going to do a bad job. So if we tried to estimate wage equals beta naught plus beta 1 times experience, that is not going to do a great job because there's obviously this kind of curve in the data. So what we do instead is we estimate a slightly different regression, which is wage equals beta naught plus beta 1 times experience plus beta 2 times experience squared. So all we do here in the data set is say we had a data set that was something like, sorry, there's a guy at our door and I don't know why he keeps ringing. Sorry. One of the problems with COVID is that I'm home and no one else is home. So so if someone comes, will there be extra credit in this course as well, or for this exam? Okay, on extra credit, I haven't planned on doing an extra credit. So there is some extra credit just naturally. I'm going to drop your lowest homework and quiz grades. I might make your lowest homework and quiz grades extra credit. So you basically are getting points for doing well throughout, but they don't penalize you when you don't do well. And then there have been like homeworks that I thought were really thorough and clear. And I gave those homeworks like an extra point on the grading. So there has been a little bit of extra credit, but I hadn't planned on, I had not planned on like assigning an extra credit assignment. I think the best extra credit is just like mastering the material and doing well on the exam. So the exams are a big part of, and I think also you should not worry, because when I tell you what the curve is, I think that you will be less worried as well. But Katrina, would you email me if you feel strongly about something and I can think about it? Okay, I will, and Leanna, I will go over the omitted variables, because that was a big trap. Like about half of the students just did not get omitted variables. So that's on me. So wages, we got experience. So wages might be, $5 an hour and $6 an hour and $8 an hour and $4 an hour. Experience might be 1 and 0 and 3 and 4. And then we're going to generate a new variable called experience squared. And we're just going to, in variables, you can't really put an exponent. So we just put x2. All we're doing is we're taking x and squaring it. So we get 1, 0 squared, we get 0, 3 squared, we get 9, 4 squared, we get 16. And then we're just going to do a regression like this, reg wage on experience and experience squared. And that is going to produce a different line that will fit the curvature of the data. That's really cool. So the question was, if y has a curved relationship with x, how can we estimate a model that allows the relationship to vary between x and y to vary with x? So all you do is include a squared term of x on the right-hand side. That's all you have to do. The best decoy was include a squared term of y on the right-hand side. You almost never want to control for an outcome variable in a regression. So if that's just, you wouldn't know that exactly, but the right answer was to include a squared term of the x. Okay, questions there? Okay, then the one right after that one also, only about half got right. It was, how do we calculate the effect of additional experience? And the answer was to take the derivative of the regression equation with respect to experience. So whenever I ask, how do you calculate the effect of some x on y, the answer is always take the derivative of y with respect to x. And that derivative is the effect of additional any x, but in this example it was additional experience. And we did this exact example in class together over a period of several minutes. And I think we also did it in the review. Any questions there? I really would like that to be total, like this derivative thing is super, super important. If you ever, and I think we did this in the review as well, if you ever want to know the effect of something You take the derivative. If you want another predicted value, you just plug in the values that you have on the for x. Okay, Leanna, I am coming to your question. Oh, okay. So when we have an omitted variable, the beta estimated can be written as beta 1 star is equal to beta. So in this class, we won't take the second derivative. The second derivative is when you want to know whether something has a minimum or a maximum. To figure out if something has a minimum or maximum, you need to take the second derivative. If the second derivative is positive, it has a minimum. If the second derivative is negative, it has a maximum. If it has neither globally, it will have neither a maximum nor a minimum, possibly. That's a great question. If x2 is positively related to y and negatively related to x1, which is true. Okay, so let me find out which question that is, which is true.
Well, I do want to clarify this more part because I'm not sure if I understood it right. For the delta 1, when it's negative, does it means that the correlation between x and y is negative, or is it there's no correlation between x and y? That's what I was confused about.
Yes, the delta 1 is the slope parameter on x1 in a regression of x2 on x1. So I can, let me show you, can I back, I will definitely answer this question, which you put a little bit later, but I think it would be good for me to just back up one step and start a minute before it so that it's all clear. Is that okay, Leanna?
Yes, for sure. Thank you.
Okay, so let me just, and this also goes back to Kimberly's excellent point, which was, you got these formulas, but it's also really important to understand what each element of the formula means. So what we were able to derive is when we omit a variable x2 from a regression, the beta 1 star we estimate is the following. So we derived this in class together, but it was that the beta star that we can estimate while omitting x2 is the true beta 1 we would have gotten if we had x2 in the regression, plus beta 2 plus, I'm sorry, not plus, times delta 1. So I'm going to define each of these terms. So this is the beta 1 we estimate without controlling for x2. This is the beta 1 we would estimate if we control for x2. We also call this, I'm going to put in all caps so you can remember, the true beta. So we say this is actually the beta that we wanted. This is the beta we actually want. So remember, like, say we wanted to control we're interested in the effect of education on wages, but we don't have data on IQ. So we can't control for IQ. So we're going to get some sort of beta star, that's not the beta we wanted, which is the beta one that controls for IQ. X beta 2 is the effect of X2 on Y if X2 were included. And the delta 1 is the coefficient in the following regression. If we regressed X2 on X1, we would find this regression. Okay, so what is this delta number? This is the slope of X2 as X1 changes. So I'm just going to point one thing out that's important, because the best decoy was just to not look at the formula and notice. So the best decoy was that delta 1, I'm sorry, so there was a question that says this. When we have an omitted variable, the beta estimated can be written as beta 1 star is equal to the true beta plus beta 2 times delta 1. Bias is how far off our estimate is from the true beta 1, which is beta 2 times delta 1. And I just asked, so I'm trying to give you the formula and re-explain the material in the test. So if you were close to getting it, you could kind of put it together. But in this question, all you needed was what is delta 1, and you could have gone to the slides or your notes and said, where is delta 1? Delta 1 comes from this formula right here. And so delta 1 is the change in X2 for a unit change in X1. And the best decoy was the opposite, a change in X1 for a unit change in X2. So it's just that the delta is a change in X2 for a change in X1, not the reverse. So maybe you guys are actually quite close to getting it right, but you just kind of swap those two, which is totally understandable. The way that I remember it is that in general, when we do a regression, the parameter number tends to have the same number as the variable that it's on. So the fact that we have delta 1 is a clue that it's on. Just one sec. Just one sec. Okay, sorry. So I just remember this as it's delta 1. What is delta 1? Delta 1 is the coefficient on X1 because they share a number. And so that way I know that it's a regression of X2 on X1 rather than the reverse. Okay, so this is really important. This is, in my opinion, kind of the middle of the class. This is probably the most important kind of thing to think of, that we think about in research, is how are our parameters wrong? This is basically how they're a formula for why and how, when and how they're wrong. So remember that this is the truth. Call this the truth. And this we call the bias term. Okay. So if beta 2 times delta 1 is large, our estimate over here, our estimate, if the bias term is large, our estimate is way off. If the bias term is small, our estimate is quite good. It's a quite good approximation of the truth. So the first thing to notice is that if either of these if either of these are equal to 0, then we're good. We good. Okay. So if delta 1 is equal to 0, the bias term cancels out. If beta 2 is equal to 0, the bias term cancels out. Excuse me. I guess that works too. So we'll have some questions later on where it says, what if the omitted variable is correlated with Rx, but it has no effect on Y? Is omitting the variable bad? And the answer is no. If it has to both be correlated with Rx and affect the Y to actually produce any bias. So then the other thing that we have that we'll see in an example is that the bias, because it's the product of beta 2 times delta 1, we can say something about what kind of bias our estimate has. So let me think of a way of showing that really quick. So say we have what is beta 2? What is delta 1? You can imagine beta 2 can be greater than 0 or greater than 0 or less than 0. And delta 1 can be greater than 0 or less than 0. Okay, so then the question is, what's the bias? Remembering that the bias is calculated by beta 2 times delta 1. So here we'll get that the bias is, if beta 2 are positive and delta 1 are positive, the bias will be positive because it's just a positive times another positive. If beta 2 is positive and delta 1 is negative, then the bias is negative because we have a positive times a negative. Okay. If we have beta 2 is negative and delta 1 are positive, we also get a negative because a negative times positive is negative. And what if they're both negative? What if our x2 has a negative effect on y and our x1 and x2 are negatively related? Well, a negative times a negative is a positive. So we did this table together in the slides for this. This is really important. This is a really awesome formula. We know what we're looking for, which is we'd like to find an estimate of beta 1 that's close to the true beta 1. And the bias term is the relationship between the x2 and the outcome variable, and the relationship between the x2 and the omitted variable and the variable that we have. Oops, that was dumb. Okay, let me pull this back really quick. Okay. Any questions so far? We're going to do a couple examples of these. Actually, we're almost out of time, but I'll stick to the end for this. Any questions here so far? Is this any clearer than it was the first time or the second time? You guys are so nice. I'm glad this, but yes, and it is just true that it is helpful with multiple exposures, multiple kind of repetition is probably boring. Like when it sounds like I said something before, you're like, I got this. But for some reason, the repetition is really important for getting a new concept kind of deep. Okay. Okay, so these are ones that like weren't too bad. I think like 2/3 got it right. We'll just do a couple examples of that then, just to see if we can kind of clean this up in our head a little bit. So the next question says, say our omitted variable has a positive relationship with x1. So if x1 and x2 have a positive relationship, what does that mean about delta 1? Is it positive or negative? It means it's positive. Positive relationship. Okay. And a negative effect on y. What does that mean about beta 2 if our omitted variable has a negative effect on y? Is it positive or negative? It's negative. So to see how the variable, how our estimate will be biased, we're just going to multiply a positive and a negative together and get a negative. So we know that this bias term is negative. We're going to underestimate the true, our estimate is going to underestimate the true beta 1. Okay, so not too complicated. And I feel like most of you are right on the cusp. If you got that wrong, I don't feel like you were, I feel like it was, so what was the best decoy? The best decoy was positive. Or that, oh, this is an interesting decoy. A couple people said the bias will be 0. So I'm guessing that you thought some positive bias, some positive relationships, negative relationships are just going to cancel out. And that's not how the bias works. They don't add together; they multiply by one another. So they don't cancel out like that. That's interesting. Say our omitted variable is highly correlated with x1. Will omitting it from the regression bias our estimate of beta 1? Most people got this right. The answer is only if the omitted variable also affects y. So remember, it has to have both of these. It has to affect y, and it has to be related to x1 in order to bias our estimate. The best decoy, the decoy that got most of the people that got it wrong, was that omitting it will always bias our beta, our estimate of beta, and that's just not true. If the variable doesn't have a relationship with y, then this term becomes 0. And so beta, if that term is 0, the beta that we estimate is exactly the same as the beta that we wanted. Questions on that? Noah, Warren, Yesenia, Stephanie, Saul, Manuel. Okay. Let me see the next one. Okay. So there are a couple others, but they are kind of all of the same ilk. So I think based on what we reviewed, you'd be able to get the ones that we haven't been able to go over together. So I just want to talk about the homework for a second and the test, how the test is curved. So for Friday, I want you to go through every question that you got wrong and write it out, the question, the answer, and what you got wrong, where the right answer was and why. This is a really powerful way of learning and also of targeting areas that are blind spots in your understanding of the class. This is a really smart, targeted way of reviewing. You're systematically reviewing the things that you missed. If there were questions that you kind of got right by luck, that you were confused in the test, it's smart to do those also. I can't obviously grade you for those because I don't know which ones, I wouldn't know which ones you almost got wrong, but I think it's a really good opportunity to to pat down your knowledge and to just seek out those parts that are not super clear and make them clear to you. So here's the way that the grading works. If you go online and look at how many questions you got right, and I have to say one other thing just about the exam. You must have your camera on the entire period in which you're taking the exam. I have to be able to see that you're not consulting a tutor, that you're not in pairs. I went through and I asked everyone that didn't have their camera on to please turn it on. I noted everyone that hadn't logged in on time. On the final, that will be a really serious infraction. I felt like I was clear in the initial email that you needed to be logged in and take the exam during class, and that was really the only way I could have any proctoring on the exam. So on the final, that will be, if you don't do that, you will fail automatically. I have to emphasize that, and there's just no other fair way of doing that. So if your camera wasn't on, or you don't know how to get your camera on, figure it out, because that needs to happen for the final. And it's obviously not fair if you put it on for 5 seconds and then you turn it off. Like, I obviously have no way of evaluating whether you're consulting another person or calling somebody or whatever. So yeah, okay, so the way that you do your find out your grade is you take the number you got right, and you're going to add 20 points, and you're going to divide the whole thing by 71. And so what this basically does is it squeezes the distribution a little bit and it shifts everyone up. So for instance, the uncurved average grade was 74%. The curved average grade is, the average is 90%. So 9 people got A's, I think 8 got B's, and there was a small number of C pluses. Literally everyone on this call, there was no one that got a D or an F. There's one person that had really struggled, but they haven't been in class, and they still anyway. So everyone that's in this class right now, attending today, did really well. So more than almost 90% of the class got a B or an A. So that's really good. Equals your grade. So I think there were like 8 or 9 A's. I think there were 8 B's. And what does that leave? There were like, I think there were like 5 C pluses. Like, there wasn't a low C. It was all kind of high C's, 60, 76 and above. Most of them were like 78, 79. So that's good. I mean, I kind of expect that the grades will be at the end of the class will be similar to this distribution. I'm hoping that we can help these C pluses come up to a B. And I'm hoping that some of the B's will come up to an A. So that's my goal. And if this is a really good thermometer for just where you are in the class. If you really want a B and you have a C, just kind of where you naturally will sit in the distribution if something doesn't change about how you work and how you study for this class. And then I hope that these A's just carry forward, but I hope we keep all these A's. So it's not intended to be brain crusher. It's intended to just be really useful, important, helpful things. And I'm doing my absolute best to try to make the material as clear and methodical and studyable independently as is possible. I'm doing as many examples in class as I can. And I'm really, really, really trying hard to make this a great class. Let me pause there. We are almost out of time, and I'll just open up the floor for questions and criticisms and whatever else you'd like to share.
Will you be creating an assignment on Canvas for the test correction?
I'll make an assignment, yeah, so you can upload your document there. That's, yes, thank you. I did write that down, but it's a good reminder for me.
Thank you.
My pleasure, thank you.
Professor,
Hey,
so 2 questions. So whether we do the test corrections or not, that curve still holds in place, right?
yeah, the curve will not be affected by your test corrections. This is just gonna be a homework assignment. You get 10 points for it if you complete it.
Oh, so the test corrections don't actually affect our test grade?
No, they will not affect your test grade. So the key is if you kind of, I can't remember what you got, Ibrahim, but if you plug in your,
Yeah, I got a 41.
yeah, so that that's a very high score. I think with the curve, let me just do the math for myself.
I think like an 85. I just calculated it.
Yeah, so that's great. I mean, like to me, and just to be clear, the 41 out of 60 was like a 68. So it's going up by, you know, what was it, 85? It's going up by about 17 points or so. So here's the thing. The other thing is if I see on the final that you've got this all down pat, I will weight your final over your midterm.
Right.
So you know you can get an A. You can. It sounds like your B isn't what you're looking for. You can get an A, but it requires a real mastery of the material. I would need to be impressed. I'm really confident that you've kind of plugged whatever holes there are in your map of the material. Does that make sense?
Yeah, I mean a B's fine. If I pass the class with a B, like I'm chilling, to be honest.
Yeah. No, B's get degrees, and they're fine grade. It means that you've understood the material to a good extent. And if you don't want an A, that's great. If you want an A, I think you can do it. I don't think that there's anyone in the class that couldn't get an A in this class. The material is not beyond anyone in the class. Is my opinion, my feeling.
I have a quick question. When you say weighted, what do you mean by that?
I don't have any specific formula in mind, but say you got a B on the midterm and you curved the final, and your whole grade, you know, you say you got a C or a D on the midterm and you curve the final, you were the top grade or the second top grade. I would be making sure that you were going to get at least, you know, you would be getting a higher grade than you would get if you were merely to average these together. So I probably won't tell you, I don't even know how I will do it. It kind of depends on lots of things. If someone's like, you know, I think that there's a little bit more grace if like, I can tell you're turning in assignments, you haven't had stuff late, you have been just like kind of cordial. I'm going to try to amp you up, but there's sort of less upward lift if that's been hard, or, you know, like sometimes I feel like I do someone asks me for something and then they don't use it. And that like kind of annoys me. I'm like, well, you know. So it's grace. It's not a formula. It's like this person's really trying and they pulled it off by the end. That's going to show up in their grade. I mean, like this wouldn't work for me. For instance, let me give an example. Say someone just never turned in a homework assignment. They were always griping about the grading of the quiz or whatever. And they had, you know, lots and lots of zeros in their grade book. And then they did great on the final. I'm probably not going to adjust their grade very much. I feel like they really hadn't done, they hadn't had needed kind of engagement and respect in the course that they needed to have a privilege of having your grade kind of adjusted based on the final calculus, the final grade, the final exam.
Oh, that makes
But, and to be clear, it's not that common for kids to outperform themselves on the final. You'd have to really make a dedicated effort to really change your grade from the midterm to the final. There would have to be kind of a structural difference in how you're approaching and studying for the class, in my experience.
sense. Thank you.
But you're doing fine. The people that are asking questions are doing great. So I'm not worried at all.
Just want to make sure I keep my streak.
Yeah, you're doing great. Okay, other questions? Katrina, you asked about extra credit earlier. Do you feel like you would still like to do extra credit, or do you feel like with this curve you're feeling a little bit more comfortable in where you are in the class?
I'm feeling a lot more comfortable in the class, but I'd always like extra credit. I feel like I don't like perform well on exams. I get like really anxious and I like can't really think on exams. So like extra credit would really save me in the long term. But this makes me feel a lot better. So thank
Okay.
you.
Good. Yeah, I thought everyone did really, really well. I thought people gave forth a good effort, and a lot what clearly came through for. And yeah, I thought, wow, yeah. So I'm really excited for you guys. I'm really grateful. Oh yeah, curve, great. I'm glad you think it works out. Saved lives. I don't remember what anybody got, so I should go back and look at. Yeah, in general, everyone's going up by 16 points or so. It's a big curve. Okay, well, class is dismissed. I'll hang back and take questions for the next few minutes. My pleasure, Derek, and I'll see you tomorrow. Yeah, my pleasure. See you guys soon.